We're just about 2 months into the 2023 Atlantic hurricane season, and as we approach our climatological peak, all is quiet in the basin as of this time. We'll keep our eyes peeled in the next 5 to 7 days for some potential development, which I'll talk about right here. But first, I want to get started with Typhoon Doksuri here in the West Pacific, which is our strongest storm globally right now, the equivalent of a Category 4 hurricane that is brushing by the northern portions of the Philippines and is expected to track northwest over the next couple of days, bringing some pretty nasty weather to portions of Taiwan and even mainland China, where it's expected to make landfall as a hurricane, something they don't see very often over there. Shifting gears back over to the Atlantic, we have a couple of disturbances that we're keeping our eyes on. This is Invest 95L, which has been tracked for the last few days or so as it traversed across the main development region of the Atlantic. But as you can see here, it's a pretty disorganized mess of thunderstorm activity, some squally weather and heavy rain in portions of the Lesser Antilles, and even racing down towards the ABC Islands off of the coast of Venezuela. However, we're not expecting this to be developing over the next few days. Pretty low odds, and if that's going to take place, it's going to have to be in the next 24 to 36 hours before wind shear in the Caribbean Sea that we typically see in July really starts to crank up, especially in this El Nino pattern that we have been entering. A little bit closer to home, we have another low that was tagged by the National Hurricane Center yesterday with 20% development odds in the next 7 days. Still a disorganized cluster of thunderstorms essentially right now, and this is expected to slowly trend towards the northwest here and again bring some potentially rainy weather to portions of the northern Bahamas as well as the southeastern United States before eventually recurving back out to sea is the general expectation for this disturbance. And then, of course, looking out in the main development region, we're not quite at that point of the year where every wave is necessarily something to watch quite yet, but we do have a pretty broad envelope of moisture starting to move off of Africa. And as that gets embedded in some of this banded convection along the so-called intertropical convergence zone, could be worth keeping our eyes on in the next 5 to 7 days to see if something tries to spin up before encountering a more dry environment in the western portion of the MDR. But as of now, the season is running a little bit above average here. Since the last time that we caught up about a month ago, we have one new named storm in our first hurricane of the 2023 season to note in Hurricane Don. Our accumulated cyclone energy, our combined metric for the size and duration of storms, or sorry, the strength and duration of storms, I should say, is running just about twice the average value based on the 1991 to 2020 climatological average. But nothing in terms of major high impact storms to date because Don was basically a drifter in the subtropical, almost like a buoy, floating around for the better part of a week and a half, 42 different advisory cycles by the National Hurricane Center. It was one of the longer lasting July tropical cyclones on record, actually, and did briefly attain hurricane intensity north of 40 degrees latitude. So a pretty anomalous storm tapping into some of that warmth that we've seen really throughout the basin. And its origin was actually from a subtropical cyclone, which is kind of it motivates an interesting question of just how do we actually diagnose these. And there's a few ways you can kind of think about this structurally. What I like to do is think about where they get their fuel from. Tropical cyclones are pretty much drawn from oceanic heat. This is an example of Hurricane Teddy from 2020 that shows this. Whereas extratropical cyclones are frontal systems. This is actually Teddy as it moved well up into the northern latitudes of the Atlantic Ocean. And you see this long band of clouds draping from the center of circulation. This is basically a cold front. And these extratropical cyclones feed off of large-scale temperature contrasts in their environment as sort of their source to intensify. Subtropical cyclones are somewhere in the middle. They tend to exist in these 30 to 40 degree latitude band and draw a little bit of their fuel from each and take on sort of a hybrid structure. This was actually what Don looked like just after the time of its formation. You don't necessarily see that symmetric eye-like structure, but not the clear-cut frontal banding, a bit of a broader circulation that you tend to see in tropical cyclones as well. And this kind of motivates another really powerful tool and another graphic that you might see posted without much explanation or context on social media. And there's really a lot going on here, but I really wanted to show this off because this is the product of a Penn State professor and a Penn State alumnus, Dr. Jenny Evans and Dr. Robert Hart, respectively. This was Dr. Hart's PhD dissertation work before he took a job as a professor at my former institution, Florida State University. This is cyclone phase space. This is a way that we can use a couple of easy parameters that you can calculate in models to get an idea for what the structures of these storms might look like and kind of dive beyond what just a simple satellite tells you. This is available at the following webpage, mo.met.fsu.edu. Let's break down these parameters. The first one here, we call it thermal wind, but it's really just does the cyclone itself actually get stronger or weaker as we go up through the atmosphere? And extratropical and tropical cyclones have very different character. These frontal systems actually get stronger as you move up, whereas hurricanes tend to weaken as they go up, as you go go through up the atmosphere with their warm core structure. Our second parameter is simply asking, is the temperature around the storm symmetric or asymmetric? And this is something we ask because tropical cyclones tend to have a much more symmetry. Temperatures don't vary much in the tropics. It's warm everywhere. But at higher latitudes, we see much more asymmetry. Just think about how our temperatures behave in State College in the wintertime, for example. And based on these two parameters, we can partition cyclones into 4 different types: our tropical, our frontal systems, and a couple of distinct gray areas based on the asymmetry and the warmth at the center of that storm. And we can use model data and analyses to track these storms through time, essentially, and see how their structures evolve. This is actually a case of a hurricane that would undergo an extratropical transition process, where it starts off in this very symmetric, very warm-cored environment, starts to perhaps encounter cooler sea surface temperatures at higher latitudes, and then eventually lose the warmth that's built up in the core of that storm, essentially. And we can actually see the reverse happen in the Atlantic basin as well, where, say, a frontal system moves over the Gulf Stream, taps into some of that warm oceanic water, and goes through the reverse process to undergo tropical transition, actually, into one of these tropical cyclones. And we see this even in an El Nino year because, at subtropical latitudes right now, those water temperatures, just like in the main development region, are significantly above average for the most part. So that's all for today's Tropical Tracker. Our forecast summary is coming up next.